So having a panel discussion is a tradition now at IWOCL. I think most years we've had at least one panel. And this is your opportunity to kind of join the discussion, talk about OpenCL, SYCL, the things that you've seen at the workshop, pain points, things that you want to see addressed. This year, we're going to be running this as a fishbowl. So these people have been volunteered to be our initial panelists. Yes, exactly, voluntold. But we have an empty chair here, which is welcome for anybody to come and join them. And these people are free at some point to get up and leave if there is no longer any empty chair. So if you wish to join the discussion, please just come up. You don't feel like you need to raise your hand. Just come and take the empty chair and join in with the panel discussion. If there's no seat, then somebody who hasn't said anything for a while will relinquish their chair. No dining philosophers here. And return. You can come back if you've left. You can always come back and join the discussion. So this means that there's no microphones in the audience. If you want to ask a question of the other panelists, you have to come and take a seat here. So with that, I'll give them the microphone, and we'll switch this off so you can see in a slide being at a stadium, so you can see everybody. So with that, I will start with some questions. So it was great to hear the LSC presentation and from Qualcomm about the great work that's happening in the embedded space with OpenCL and SYCL. But it's really difficult to kind of get insight into what applications are doing, what an embedded device really looks like anymore. I know, Lucas, you made some comments around really they're just as powerful as a desktop GPU now. So my question to kind of start the panel off is, what is embedded? What are people working on? Is everything solved? Big challenges still there?
Yeah. So I think I mentioned a lot of things in the talk. So Qualcomm is really getting into this edge AI space. So we have lots of chipset. Actually, lots of them are small, like low end. I don't know what GPU they're running, but so the idea is really I think the large language model, this AI, Gen AI stuff. If you look at this training stuff, is already kind of reached a stage that relatively very stable. So there's a discussion saying like, oh, we already run out of all the materials that can be used for training now. People are doing like a simulation, kind of simulate the physics, the whole world in some way to supply new materials for training. So from the edge AI perspective, yeah, that's actually a good thing for us. So it means that the model is much more mature than before and can go smaller and can run on the low end devices. So from our business, I mean, from GPU perspective, I have seen like a request from these IoT startups. They just reached to us after they read the blog about the GPU running large language models, and we have seen like an automotive team. They also, internally they reach us after reading the blog. We didn't advertise like internally to many people, and they just say, oh, we needed to have them running in the edge space. You think of like from the cost perspective, right? You don't have to pay $20 to the chat, OpenAI. Most thing can run locally. You can target the very specific use cases. So this is a great opportunity for Qualcomm and also for our GPU team. So we started this project last year, and so right now we are super busy with some requests. We try to enable much smaller models for really old GPUs. Again, open source versus closed source are proprietary. So the open source has a lot of advantages. So the developer can just go directly to run on their devices, and only they reach to us if there's some issues. So our support effort is much smaller, So we see great opportunity. And again, I mentioned the IoT. I mentioned the automotive. I also mentioned earlier, this compute we call Windows, we call compute product, which means it's the Windows on Snapdragon, the ARM CPU running on ARM CPU. So they also reach us, trying to have some, models enabled without doing too much work. Yeah, so we kind of, again, as I said, yeah, we are working on this really old, we try to find some old devices, so that's what's happening in my team. So yeah, I think, yeah, again, startups, people have seen like lots of AI startups, working on this, enabling small model, very dedicated use cases. I think great opportunity. So if you have some like a really brilliant idea, think of, yeah, so that's, I think, yeah, maybe 2 years from now, you'll see really smart low-end devices that can talk to you, can generate really customized results for you without too much cost. Yeah. So
I think from my perspective, if you look at these embedded devices, the GPU architecture, for example, isn't that much different than from what you see in HPC. You still have these work items that are then collected in work groups or blocks or threads, whatever you call it. I think there's other details where it's different. Like on an HPC system, you typically have the GPU as an accelerator that is with its own memory, and you need to transfer data. Whereas if you look at, for example, all the hardware that was intended to go into cars, for example, you usually have them as an SoC, and the GPU and the CPU, so the host, basically share memory. So you also want to leverage that fact, and because you have less powerful resources, you also want to leverage the resource that you have as much as possible. So for example, if you execute on the GPU, you potentially want to also execute on the CPU at the same time. I think a lot of this is already possible with SYCL. We just basically also keep it in mind when we design APIs to make sure that things like, we don't always only follow the model that we're used to, but also keep in mind that there might be devices with like different trade-offs in terms of like device management and things like that. And for AI, I think the quantization of models is much more important. So you will see much smaller data types in those systems, and these custom data formats need to be supported. When we're adding, we have half now. We have the SPV working group working on BFloat, for example, and also on smaller models. And I think that's important. I mean, for a data type to become fashionable, it first needs to be in hardware, and hardware development cycles are not super short. So I would say there's still like usually time. It's just important that like the vendors, the hardware vendors converge on something like these block scaling formats, this MXFP4, MFXFP6, they were basically now kind of standardized between different vendors. And I think that's a good point where people can go ahead and say, well, let's put this in SYCL, let's put this in SPV, because apparently a number of vendors have agreed on this is a good format. This is what we want to support in hardware. We should probably not run after everything that some AI hardware startup comes up with and puts it in 2 bits or 1.58 bits. And this is paper that put everything in 1.58 bits. And I don't think you want to standardize that right away. What the SPV perspective is.
I kind of think of the AI image formats as being, sorry, the AI data formats as kind of being the new equivalent of what image formats have been in the past, where there's definitely been, I guess, eras of different image formats as well. And some of them are still with us today. And some of them really aren't using anymore. Like, who remembers paletted textures like back in the day? You never hear about those anymore. So some of them may go away. And there will be new ones all the time. In the cases where we really need to move fast and maybe somebody is experimenting, this is a perfect opportunity for extensions or vendor-specific extensions. get them out there quickly. And if they are popular, then they become standardized. If they're not, then no harm done.
Yeah, so the hardware cycle to add a new data type is really long, actually, relative to software. You can always pack things through software. And in hardware, like 2 or 3 years, from this prototype proposal to the product, that's really, a long cycle. During this time around, this kind of cycle, you don't know what happened in the research community. Maybe it's like a 1 bit will be enough, or some crazy new, maybe even better than transformer. Today transformer is the king, but who knows? Maybe 1 year there's new. There are already like a new ways to improve attention mechanism. Yeah, lots of things could happen. So I think for hardware vendors, we are relatively play safe. Yeah, because adding hardware blocks is really expensive. I mean, from design verification all the way to software support. That's a big thing. Like even some don't mention data type, but even some small blocks, some small instructions, adding one is time consuming actually to see the real benefit. So I think yeah, again, for most hardware companies, yeah, I think we kind of behind what's happening in the software in the research community, but that's pretty normal. I'd say, yeah. But agree, yeah. But this, yeah, we definitely should, if it's proved very useful, like for LP8 or some, we should move fast to standardize that. So.
LP64, that's it.
Yeah, so first, yeah, I think yeah, LP16, LP8 right now, I think it's the yeah, we try to.
Maybe one thing to say, I think in the HPC space, we'll finally maybe move over FP64, because I think it is maybe something a little maybe lacking in our community. It's like we know floating point number, we don't really care, right? We just put FP64 everywhere and we are good. And see if we are fancy, we move something into float, but we stop here, right? And nobody really do, at least a few people do any kind of statistical analysis to know the precision they really require and all this kind of thing. And hopefully we will move forward a far better understanding of our algorithm, which really data structure we should really keep in 64, which one can be moved to bFox16. Maybe stop using int for your loop and start, do this kind of thing. So maybe we'll move forward. And I think we'll be forced, because in the future, nobody needs FP64. HPC is kind of not dying, but I think scientific computing, nobody care, right? So the vendor will just emulate FP64. So you will have a ratio of 1 over, I don't know, 20, 30, something like that. So we'll be forced to try to move as much as possible to lower precision, because this is what the hardware will detect. So I think it is one of the next evolution in HPC is like this lowering precision for some algorithm. And I think it will be some nice development and opportunity to develop new algorithm and new tools to be able to do with that. So I guess it's if you're a young researcher, I guess this is the future, this kind of thing.
I guess one of the challenges with any new data type like BAPO is developing the CTS tests to check that the numbers behave correctly out of. Thomas, you've been working on complex for many years and trying to figure out, from performance test suite, what it means to say complex behaves correctly. Or CL has worked for a long time with its, a lot of the mathematics with good precision. And so the CTS stands the test that do the usually on all the match lines. So how do you think that and a strategy to testing may change through these adoption that you text on?
Yeah, I think floating point number arithmetic is this kind of thing. The more you know, the more you are surprised that anything work, right? Because you're like, it should never work. It is impossible. So I think it's very complicated because I don't know, for example, right, you have +0 and -0. And in theory, if you really want to be compliant, when you multiply by 0, the compiler cannot optimize away because you need to keep the sign of the real 0, all this kind of crap. And of course, a lot of compilers don't care, right? You compile with O2 or fastmass, and then you do crazy things. So I think it's really not well defined. I mean, it is defined if you already follow IEEE 775 or something like that. But most of, at least in HPC, nobody does that. It's too slow and all of this kind of thing. So we are already in kind of on-wavy, good enough. So I think it will be nice if we have far more kind of a clean definition, because I think it will be required for the future to lower. Because right now, if not, yeah, I guess. BFOX 16, I have no clue how they do, I don't know, cosine or stuff like that, what you should expect or this kind of thing. So I think we may need a few standard or stuff like that. Yeah.
I mean, I kind of think of this in jest, but in some ways, the traditional conformance for these AI data types, it doesn't matter as much because you're feeding them into these big matrix multiplication engines that are doing operations in some implementation defined order. You know, as long as your model converges at the end of the day, you're good enough. So in some ways, I think we need to rethink how we do conformance testing for some of these AI data types, especially when we're using them with matrix multiplication engines, because the old strategies don't work anymore.
And maybe this is a problem, right? For example, at Argonne, we have still some people who arrive on our machine and they want bitwise reproducibility. On 10,000 nuns, 60,000 GPU, it start to be hard to be sure you do everything in the correct order and everything, but some people still want that. And so how can you do that? For example, if BFLOX system, maybe even an ad will be random because the hardware say, yeah, whatever, I can do some stuff, right? So I think it will be a lot of adaptation as a community to accept this kind, maybe, or to push back and to say, oh, we cannot do that. We should emulate rigorous whatever, and we can take the heat penalty because it's too hard for our algorithm. So I think it will be a big development in the, as HPC following the new hardware trend, because we are not setting it at all. We are just big follower or whatever. Yeah. And I think it was like the C++, right? We use C++ now, not because it's a good language, right? It's just because Google spent billions of dollars optimizing to death and it was fast and we were using it, right? So I think it's nothing, it was the best language at the time or whatever. It was efficient. We are using it. And I think we'll do the same with the hardware. We'll use BFLOX 16, not because we like BFLOX 16, but because the hardware of BFLOX 16 and we should just use it to be, this is our original choice. So.
Yeah, so this AI models, like sometimes we use perplexity score to measure how good the quality is. But sometimes we see like a better perplexity score actually doesn't mean the better quality output. So agree with Ben that yeah. So this we should rethink the what's the requirement for this AI centric conformance test. So it kind of remind me this OpenCL, this traditional graphics. You don't really have like a bit exact conformance test. Many people use this visual, like just see like there's no like some distorted output that might be fine. So maybe TSNR to some extent that's okay. Similarly AI, this output large language model, this kind of thing we can think of something similar. Yeah, don't have to be super strict. Otherwise, yeah, it's really hard to pass tests. So yeah.
Hello, everyone. So what I can imagine to be quite a difficulty with all of the AI data types is that they are very specific to hardware. Sometimes only one chip of one particular hardware generation supports this special data type in the tensor cores or matrix cores. And to be able to test this, you of course need a sample of the hardware to test it, and you also need to write it in emulation very, very strictly, and make sure that for floating point this gets really complicated, because all of the edge cases have to be modeled correctly in emulation. And once there's a mismatch, even a small mismatch for rounding between the actual hardware and the emulation, then the test is not really functional anymore. So it gets really complicated really quickly. And as extensions, maybe it's beneficial to add the flexibility, but OpenCL and SYCL are designed as really cross-platform compatible languages, and adding support for a specific format that only works on one particular chip that might even be super expensive. Of course, it's a benefit to have it, but then the code is not cross-compatible anymore. Especially if you can't really emulate the data type. If it's like in NVIDIA's TF32, this 19-bit format, you can't really emulate it, this efficiently on a CPU. I mean, you could do it with higher precision, but then it's not the same thing anymore, and it behaves differently. So it's very difficult, and it takes a long time for such standards to manifest in sufficient many hardware chips to be really considered for adoption in a general way. A story for that may be the dot product for accumulate that might have crossed already the boundary of being adopted across the majority of hardware nowadays. For NVIDIA, it's been present since the Pascal generation, and in the new ARM and Qualcomm chips, it's present, and in the new AMD GPUs and Intel GPUs, it's also present. But there's still some old hardware around where it's not present. NVIDIA 900 series, and those GPUs are still around and it's not present, but it still can be emulated at least. The tricky thing here is that using this in OpenCL becomes a bit of a mess, because for Intel, for example, we are using the proper extension for it. For AMD, you need a call to the specific GCN hardware function for it. For NVIDIA, you need inline PTX assembly, again, because they don't support the official extension. For ARM, there's another separate extension for it. So you need all these preprocessor switches to switch between the device-specific function calls to use it everywhere, and then you need a fallback in case it's not available. And for DP4A it works, but for the more complicated matrix data types, it's really, really difficult.
Okay, maybe moving the conversation then on to pain points of applications. We've seen a lot of people present so far at the workshop about applications. So what does our current Padders think about? What are the pain points for building, developing, debugging, all the tooling that they need, hires everything for really working efficiently with OpenCL, SYCL, and go on with that and continue the main ways.
Yeah, I can go. Yeah, so one of the top customer complaint is our tool debugger tool. So profiling tool. Traditionally, we haven't really. Yeah, this. I mean, Intel, other NVIDIA, AMD, they have much better tools than Qualcomm. So we're trying to play catch up. Yeah, this debugging. Profiling debugging. I mean, it's GPU kernel debugging itself is very complex, and if you don't have good tool, yeah, let's make it life a lot harder. So we are trying to improve on that front, and I think there's also like open source tool that, for example, this interception, like Ben did this. Yeah, this is also very useful tool. So I think maybe we should think of more like in a standard working group. Maybe we should think of how to have some like whatever function or some maybe standardize some of this tooling. That would be definitely helpful for the developers. Yeah. So I think we have a tooling call, OpenCL tooling call, but I didn't participate. I don't know. Do we have any? I don't know who's joining that meeting regularly.
So yeah, I can talk a little bit about the tooling call. It's mostly for compilers. So things in Clang and this Ruby Illuvium translator and similar to that. But I think we're kind of avoiding the elephant in the room, which is, and Moritz alluded to this also, the biggest pain point is the different levels of support in different implementations. It's hard to have a standard if there's so many optional capabilities, and in the same market, there's some that are supported and some that aren't. And some of those are even behavioral. Like, I think enhancing the CTS suite has helped a lot. Could always be better, but at least we can have some confidence now that when an implementation does advertise a feature, that it's behaving similar. Again, could always be better, but the bigger pain point for an application is just that you can't rely on an extension being universally available. One other one I've heard several times at this conference, so maybe if people have ideas how to fix it, this is maybe a little bit more SYCL based, is just a distribution problem. So how do you ship an application that uses SYCL? I see some nodding if anybody else wants to come up.
Those that have to ship SYCL application, to relieve one of our panelists and kind of talk us through the things that they wish SYCL and the whole environment would do.
Yeah, the challenge with shipping SYCL is actually very different from shipping OpenCL. And both have their unique challenges when you're actually shipping what we are doing end user applications. That is something where an end user would just download a single binary and run that and not be expected to install additional dependencies in that are otherwise required. So just like you would, I don't know, install Slack or something on your desktop, you could just download something that uses SYCL or uses OpenCL. And with OpenCL, we had there's always the problem that you actually compile the source code on the computer, on the user's machine. And so you can't really predict if the compilation actually will go through. And the various implementations would sometimes even just fail compiling on that version of that user. So in order to fully test it or actually fully ship it properly, you would need to have machines of all these types to actually just compile and see if it even compiles on that machine. Sometimes requiring hardware to install the driver even and to run it to get to that point. With SYCL, typically you can compile ahead of time, and the source code is being compiled down to an intermediate language. So at least you can be reasonably sure that the compilation stage is already done, so you don't have to ship source code, which for some vendors was also a problem. Like, they would not want to ship source code because they have trade secrets in it. Just something they don't want their competitors to see. So shipping source code was not an option for everyone. And so with SYCL, at least you get an intermediate language and you have that step behind you. The problem with SYCL and shipping SYCL applications is more on the library side because there's no ICD. In the same way that you have it in OpenCL, where you can just have the driver bring the runtime libraries. Instead, you have to bring it yourself. And it's not really interchangeable because the C++ ABI can easily break. So it's nothing, you should typically ship a DLL, but there's no point in being a DLL. It could be statically linked and smaller through static linking if it strips away unnecessary features. Because the DLL itself does not have much of an advantage. There's no point in replacing it with a different or newer version because it might just be incompatible. And then depending on which implementation of SYCL you're using, then it's the backends and runtimes have their own dependencies. You have to prepare for some DLL that you try to load failing to load because there's a dependency for that one missing. How do you handle it from your application? Do then as you as an application completely want to stop loading? Probably not. Let's say you write something like Photoshop and you have a plugin that does an image filter based on SYCL, and that plugin fails to load with a DLL missing. Do you want Photoshop to stop loading because of that? Of course you don't. So these are the things that an ICD made easy. Any ICD would just say, yep, sorry, no no implementation here, and your program would still run.
Maybe also my perspective on pain points for from the application side is someone who works a lot with OpenCL on application side. The good thing is with OpenCL that you only have to write the code once, but the bad thing is you still have to test it multiple times on every hardware where you want to deploy it. The thing is when I implement a new feature, for example, on an Intel GPU, and I test it on the Intel GPU and make sure that it works, then it works on the Intel GPU, and with some luck, it also works on other GPUs, but there's absolutely no guarantee. And it might not work on an NVIDIA GPU, for example. Most of the time, the reason for this is doing things that are not entirely safe with compiler optimizations. And the behavior of compilers is different regarding the optimizations. One example is when you disable the checks for floating point numbers being not a number, which means you guarantee to the compiler that you never divide by 0 and then do crazy stuff. When you check a number, then when you check two numbers to be one smaller than the other, what the compiler then can do is invert it and check for greater or equal to and invert the result of it, which is valid as long as all the floating point numbers are valid. But as soon as one of the numbers becomes not a number, then the check fails suddenly. And this is one of the things that some compilers do this inversion for optimization and some don't. And if you don't test this on all of the hardware where you want to deploy, then it can slip through, and suddenly it doesn't work on one of your customers' machines, and that's a big risk and a huge pain point that I always need to have all of the different hardware available to me to test it literally everywhere to guarantee that it works everywhere, because there's a high risk that it doesn't.
So I'm too tired to be polite. So, but I think the pain point are just the lack of support everywhere. I mean, everything is buggy. Every time you try your apps, you run somewhere, it will be broke, right? Nothing works at the first try, ever. The CMake is broken. First, you spend 20 minutes fixing the CMake. Then it is some complaint flag that you put ML, LVM, whatever garbage is not supported. And after you switch, it's just a nightmare. I think the lack of, on the slide, it looks good, it's portable, but when you really try, you have a full application with a lot of stuff, is really painful. So I think it is. When I will be president of the world, I will do a ban of all the hardware. And for 10 years, no more hardware, and we'll just focus on the software, and that's it. I think the problem is too new stuff. People want to do new stuff and not have the basic really pinned down. And I think this is the thing. I think a lot of people do a lot of half-baked stuff, right? Because this is fun. Everybody is human, so it's prefer new shiny stuff and everything, but it will be nice if we can just focus on the basic, define a set of basic, and this one should work everywhere, right? So at least as an application developer, you can make the call of, okay, I will just use this limited set of features that I know are really portable, I can use everywhere. And maybe as a committee, we should be far more open to say, okay, these features are passing, these features are correct and everything. So maybe as a SYCL, it's just not too many implementer or stuff like that. And maybe if we have a good CTS with a lot of vendor, we can have the good problem of just if you use extension, maybe it will not work. Whereas if you use anything, maybe it will not work. So sadly, so if you use really basic stuff, it should work, right? But as the thing is it's not clear what it is an advanced feature that may not be supported and what is really a thing. You can malloc device and submit a parallel for in the range. This one will work everywhere. But as soon as you use, I don't know, Daniel show atomic ref with a weird, not even weird, but it's like a scope. It will mean not supported on AMD via Intel because reason. So I think this is a main issue, honestly. But I think, yeah. So this is a bad part. The good part is you should report the bug, please. I know it's painful. I know it's a lot of work. I know when you have a bug, you just want to forget about it, to block the warning, the workaround, and move on your life. But if you don't report it, we'll not know, the vendor will not know, and it will never be fixed, right? Because you just hope that somebody else will do it for you. Because, yeah, most of the time the vendor, they don't, for them, everything is fine. They don't have bug, it works, it's cool. They implement new feature because whatever. So I think, yeah, it's really important to report bugs. Some bugs are difficult to report, some bugs are super easy. For example, if your compiler prints this nice warning with internal compiler error, this one is super easy to report. You just give everything and nobody can complain. The compiler should never ice. So this one is easy. Some of them are far more complicated, but yes, please, you do diligence, report the bug, and after you can sleep good at night. You did the correct things. And if it is broken, at least it's not your fault. Where if you find a bug, you don't report it, it's a little your fault if it is still broken because you didn't do your part. So
yeah, one more thing I would like to add to the shipping and bringing software to end users is again, one of the differences between OpenCL and SYCL in that regard is the compile result that you ship with SYCL. Since you don't ship source code, you have something that is to some degree machine specific. It could be SPIR-V, it could be a different intermediate representation. It gets tricky when you're working with a hardware vendor where each hardware generation or even each chip has its own separate binary representation, and you need to compile for many of them because there's no common intermediate that you could use as a like, I ship this binary for the vendor and the driver will take care of making it work with that. At the same time, if you have this one intermediate, it's hard to do architecture specific optimizations where you have things like you would want to unroll loops differently or alignment and all of these things that may easily change between hardware revisions even. These things then are tricky how to ship that. Because if you add too many binaries, you end up with a really, really bloated thing. And yeah, we're not at a point where we have like either what we had was Java bytecode or we have x86 and ARM. And that's sort of on the CPU side, it's almost all that we care about. And it's much more diverse in GPUs. And it's still sort of an open problem. How do we ship this in a reliable way that is neither bloated nor too restricted?
Well, I suppose I only need one chair. I suppose this was the call for the adaptive CVP generic JIT compiler, because I think this is kind of a solved problem as far as device images are concerned. You can totally build a SYCL compiler that has a single code representation, and you can still specialize code in there. We have a reflection mechanism that allows you to at JIT time test what are you JITting for, and then let your code behave differently. So where I see the issue is actually not with the device binary that you generate, it is with the handling all of the specific backend dependencies. At some point, something the user needs to provide, at the very least, the kernel driver, but maybe also your SYCL backend is linked against a particular CUDA installation located in a particular directory, and maybe this is then located on the target machine somewhere else. And this goes back to the deployability question, of course. And this is, I think, very difficult for SYCL because it's totally unclear where to make the cut. And we could make the cut at arbitrary locations, but I don't think anybody at the moment has a good idea of what would actually be the best decision here. And this makes it difficult to really commit to one particular deployment model. Anybody else?
Yeah, so maybe it's not a big topic for discussion. I'm just curious, and it's in a way a continuation of my question from yesterday. So I have a sort of question to our, well, dear guest from Qualcomm, Chan. So you have presented some work which Qualcomm team was doing, which your team was doing. You, of course, are a representative of your big and small teams. And I have seen a lot of focus on OpenCL, quite future plans for Vulkans, but I seen nothing for SYCL. So could you please comment on this? Do you plan to go to the SYCL topic at all? Or we would not expect something on the SYCL topic from Qualcomm, for example, in this and next years?
Yeah, so I mentioned yesterday, I'm a super fan of OpenCL. So been working on OpenCL since I joined the Qualcomm GPU team in 2010. Yeah, so for mobile, devices, we care performance a lot. So we're not like a desktop GPU or this laptop GPU where you can, reasonably good. The kernel is, running fine. It's that, we really squeeze the performance to the really low level. So OpenCL is the, gives us a lot of flexibility. So we can actually embed in our assembly into the kernel some way. And lots of this highly effective ways to do the optimization. I'm not a SYCL expert. I try to learn it, but my understanding is that SYCL relatively high level. So it's probably quite easy to deploy, to have a, to finish the development work. However, the performance optimization is relatively harder than OpenCL. So again, we try to, get it as much as we can from the silicon. So that's why my team has been really focused on OpenCL, and we help customers on OpenCL. About Vulkan compute, yeah. So for game studio, like gaming companies, we Vulkan compute is the way to go. They also offer very similar level of optimization to like similar to OpenCL. We can do a lot of like low level optimization. About SYCL, so I'm not in a position to tell much about the plan, but we are looking into it. But for very probably specific applications where the performance is not the highest priority, maybe we have a lot of redundancies. Like yesterday, I mentioned like the reason why people are suddenly interested in the GPU is that because in the IoT devices, in the automotive devices, they're redundant. Like they don't use GPU as much as in the mobile space, because they probably running on our like this NPU or other modules, so they don't have rendering, right? So this GPU is free for you to run large language model. So for SYCL again, we see some opportunities. So for example, a similar situation, right? So if your GPU is idle and people want to already have some SYCL applications, they want to port it, or CUDA applications, they want to port to SYCL platform and to run Arduino. That's possible. Actually, we have some scenarios that we're I think that Qualcomm, yeah, is looking into. I don't know the real business plan, but I can tell, yeah, we're looking into it. So yeah.
Yeah, so I understand your position on like performance, OpenCL, more opportunities for optimization because it's kind of lower. That's SYCL, that's understandable, right? It's just that I'm thinking more like about adoption opportunities. I mean, if applications have no OpenCL support, then naturally how you would use Qualcomm GPU, where And it's not like on performance, it's not like without OpenCL you could use it slowly. No, you can't use it at all. And for example, I could talk about Blender, but Blender don't really have any plans to go back to OpenCL, but at least it's have a SYCL now. So that's one of the things, one of the scenario. I don't know how representative it is, but that's definitely at least one application with such situation.
I think one question here that comes to mind when with regards to SYCL is, what does it actually mean for a vendor to support SYCL? Because SYCL is kind of layering itself on top of other APIs. So if Qualcomm, for example, said, okay, we're supporting OpenCL, we support SPIR-V, and the OpenCL features that SYCL compilers need in order to be able to run, then existing SYCL compilers are just going to work on the hardware, right? And the same thing if the hardware vendor has some other API that they, for whatever reason, happen to like more than OpenCL, a SYCL compiler could just target that. So is it really necessary for a hardware vendor to come forth and develop their own SYCL compiler? Maybe it's sufficient to just continue working on their own existing OpenCL implementation and say that they also support SYCL. Or maybe they contribute one particular backend, a new backend to an existing SYCL implementation or something like that. So I think we maybe need to step away from the point of view that is prevalent in the OpenCL world, where every vendor needs to provide their own independent implementation, and instead kind of more converge on a view where the community provides support by layering on top of what vendors give you in terms of APIs.
So I actually have slides to both of you. I start here. Well, from the point of view of SYCL user, I would say it matters actually quite a lot what vendors support, because if vendors commit to something, we can kind of expect some level of bug fixing, support, and such for community. It is always good when it is, but it is a bit harder to really plan that, okay, this project that is run by a research group at the university will be production year ready for the next like 5-10 years. Obviously, vendors always drop support, but usually it is somewhat a safer bet than a single research group. Again, not that it is necessarily bad or good, but that is kind of the optics and the impression. And I think the fact that SYCL is now supported by only one major vendor is kind of a problem in how it is perceived. Because, people perceive vendor-based implementations as more serious. Not necessarily better or something, but it is seen differently than community things.
Okay, about LLVM, about the LLVM compiler infrastructure.
I'm not saying I think that, I mean, but I'm saying that it is perceived this way. And I mean, I have seen in many places that people prefer, for example, Intel or NVIDIA compilers or Cray compiler shipped with their system over vanilla LLVM. Because it comes with some kind of warranty tag. So because also it's not about that this is broken, it's more like if it is more or less likely to be broken. It's more like if it is broken, I know those people are to blame and they will fix it. With community, it is more like, probably they will fix it, probably they will just help me fix it.
So I totally agree with you. And as a user, you have some power, right? As a user, believe it or not, I know it's weird to believe, but sometimes vendor listen to you, right? If you go to of your supercomputer or whatever, we say, I need SYCL, those people will try to buy support via code players or company. And this is how it starts, right? It starts by, and to go to the point of Axel, people throw LLVM because LLVM is supported by 10,000 billion company, right? LLVM is not one guy. LLVM is Google, Meta, whatever. Everybody is doing LLVM. National Lab are putting code in LLVM. Everybody is putting LLVM. And so I think this is, as a user, what you need to do. You need to be vocal on your sister, on your support ticket and everything to say, okay, please it's broken, you should fix it, right? So I want that, it is important, put it on my code. You support Fortran 77 for 40 years, so now please start to supporting SYCL. And so I think you should do that. So you have some power of improving that.
Yeah, so maybe I can answer the question earlier that you asked about this Blender, all this, doesn't go back to OpenCL. So as I said, so we are, Qualcomm now, we have entered this laptop space, right? Compete against the Intel and the AMD. We also have a strong presence in the automotive space where a lot of platforms actually have multiple GPUs. There's some redundant, computing that we can, maybe we don't have to care the performance that much. So for SYCL, again, my perspective is that for mobile space, in a mobile or embedded where you need the final 1% performance, SYCL may not be the best API for this use case. But again, for something like automotive or for this laptop or even gaming laptop or this high-end laptop, products, SYCL, I think there's a hope that the Qualcomm may support. But yeah, we will see. Yeah, maybe, we'll have some product. But so the other point I want to make is, I'm not a compiler expert, by the way. What I heard is that to make SYCL work on Qualcomm platform is not, GPU is not hard. The hardest part is actually to make it performant and also to support all the key extensions that OpenCL support today. That requires a lot of efforts. Actually, that's not a small part thing for the team. Again, Qualcomm GPU team is relatively much smaller than the other companies' GPU team. So we are really, if there's a customer, like a big customer asking you how to have this SYCL support, otherwise I wouldn't buy your product. I think we'll do that immediately, but otherwise we try to play safe and yeah, it's also a resource kind of constrained situation, yeah.
So now coming back to the question of community-provided SYCL compilers, I think we need to distinguish between community and between non-commercial, and those are not the same thing, right? I mean, LLVM also is a community, even though a lot of companies engaged there. It's just that I'm saying that it doesn't necessarily have to be the hardware vendors. Somebody needs to put in the money. Yes, it's good if there are also commercial actors involved that you can then maybe negotiate a support contract with. But that does not necessarily have to be the hardware vendor. And Codeplay has done that for NVIDIA, for example, with the One API compiler, right? So none of that requires involvement of the hardware vendor, as long as the hardware vendors provide something that SYCL can reliably tie into. And of course, what they provide, be it OpenCL or something like that, can also change after some time. I mean, there are a lot of hardware vendors where we can actually observe them shifting strategies, now we're doing OpenCL, now we're doing HIP, now we're doing whatever. So just having a hardware vendor involved is also not a guarantee that a programming model will be still maintained as top priority 10 years or so in the future, right?
Yeah, well, I'm a bit surprised to see that Codeplay is kind of not a hardware vendor because, well, I mean, Codeplay is acquired by Intel. And he is getting tasks from Intel, so it kind of goes there in this direction, even if indeed Codeplay as a separate company, not produce hardware. And I did just wanted to say that there is indeed this gray area of engineering resources, because indeed engineering resources are money, it's work hours, either volunteering one or a paid one. And SYCL here is kind of indeed high level enough to have several layers. So for example, we could say that Qualcomm could go and have a SYCL backend. Well, I mean, OpenCL backend is already there for SYCL. But then if something not working very well between SYCL frontend and then OpenCL backend from Qualcomm, who should fix it, right? Who should put effort? Should it be a Qualcomm team? Or for example, it should be adaptive CPP or One API team from Intel? That seems to be unclear. And I guess this is why collaboration be breaking apart here.
I would also like to mention that, again, we do collaborate with some hardware vendors, and also some hardware vendors, won't mention names, deliberately refuse to work on anything related to SYCL. So yeah, we use SYCL to run their hardware, but they refuse to touch this code on principle. So again, I'm not politics. They have their own software platform, they're promoting it. And yeah, again, does it make sense? I think not. Is it something that happens and that influences the public perception of SYCL, that it is like second-rate thing that vendor are not touching with a 10-foot pole? Yes. And actually that kind of brings also vendor support to what I want to reply to your opinion about SYCL, that actually we switched from OpenCL to SYCL specifically to get better performance. Because as a vendor, you have more control over OpenCL. OpenCL in HPC world now is not the primary target for many vendors. And with SYCL, you can easily interoperate with native stuff. You can just put with ifdef in the kernel call to any intrinsic and it will work. So it actually allows us to get that 1% by when necessarily trading off compatibility for vendor-specific intrinsic. And with OpenCL, it is not possible. Again, I suspect as a vendor, you have totally different balance in this case, but for user, it is the other way.
Yeah, I guess really it's vendor dependent. So we spend a lot of time optimizing the OpenCL solution. So yeah, for us, internally, if we have some fancy feature, even graphics related, require some complex kernel or shading language, we usually do OpenCL because of the ease, the ease of use and also the performance you can add in assembly to it. So again, I guess really vendor dependent. Not some vendor maybe their OpenCL solution is probably way behind on some performance optimization, but this is not true for Qualcomm. So OpenCL is the last 15 years is the mini compute API that our customer have been using. Like I was joking, like when you if you have an Android phone powered by Qualcomm, when you take a photo, shoot a video, a lot of things actually OpenCL are running behind. So there's denoising algorithm, there's this pre-processing, post-processing, all kinds of things are running with really good high performance. We have some ISVs, this super good at optimizing OpenCL for Qualcomm platforms. So this whole kind of small ecosystem for Qualcomm OpenCL is relatively mature. I mean, if we move to SYCL, that's another a big monster. If we have to teach customers how to program SYCL, how to use extensions this way, that way, that's a big investment. So again, as I said, right? So I think we have seen some opportunities. Use cases like automotive or some other even compute platform. If there's a redundancy in terms of GPU, performance, it's possible. But again, as I said, mobile space is a totally different space. Yeah.
I just want to add something about the whole OpenCL on SYCL and so on. I think from a Kronos perspective, we are trying to work on the integration of those things. We have public extensions which are aimed at supporting SYCL. I think OpenCL should be the favorite SYCL backend. For the only reason that it solves the issue we were talking previously of distributing SYCL applications, because you have an ICD loader under your OpenCL driver for SYCL that will allow you to multiplex and see if you have a platform and devices. So yes, OpenCL has been pretty much abandoned by some of them. But if we look at SYCL, that is going to put an OpenCL implementation in every Linux laptop and every Linux server on the planet, OpenCL will become very much a target of choice. We are putting extensions to implement the other programming models. So we implement HIP and CUDA on top of OpenCL nowadays. So an OpenCL is way more flexible than it used to be, and we are working hard to try and make it so. And also, we are trying to implement OpenCL on top of Vulkan that exists already, and a lot of people have Vulkan drivers, and the performance are not so bad. So we are working, and of course, we're open standards. We move maybe a bit more slowly than users would like to, but I think we cannot discard in the future OpenCL being a very good target for SYCL. And it may be a very exotic OpenCL on top of a Vulkan driver, but that is definitely something I can see happening.
Just one, example. For example, vendor-specific MPI, usually tied to vendor stuff. So, kind of, sorry.
To continue on the OpenCL versus SYCL question, and should OpenCL be the preferred backend for SYCL? Well, I like OpenCL. I'm not against it. Just something to think about. On the Blender side, we had to specifically prevent OpenCL loaders to load, because ICD systems is nice, but it's quite open, and it's frankly very common to find end-user systems that are completely broken, OpenCL enumeration or OpenCL implementations that when SYCL runtime tries to use these, that would still lead to crashes in the process itself. And where I have a few offensive cases, like the old Intel OpenCL CPU runtime, for example. We can find cases in field where, things just break. So I'm not saying that we should not think about implementing over OpenCL. It's a good language, good abstraction layer, but just don't think it's all rosy and ICD loader system is perfect, because you can quickly run into issues in real life, because any vendor can break it, and everybody did it.
So yes, some vendors ship OpenCL drivers that may conflict with OpenCL drivers of their next generation or something like that. We've seen this kind of thing. Disclaimer, I'm the developer of the ICD loader on Linux. So I know the subject quite well, and we had to jump through a lot of hoops at the beginning. These are things we are looking at to improve in the ecosystem, find ways to be able to blacklist all versions of drivers or things we should be looking at, find ways to help with these issues, but they need to be reported, and then we need to find a way to address them. Sometimes it's in the vendor's hand, and there's sometimes not much that can be done indeed. The user has to manually intervene and fix the problem. So, I mean, if its loader is crashing, but not much you can do. But aside from that, we are offering layering solutions, so you could filter platforms that you want. There are lots of things which are now possible in OpenCL and very much easier than it used to be. Not saying that it is perfect. I'm saying that I expect it to become more prevalent in the future, and that people will have less intensive to go to maybe vendor solutions for their OpenCL, because there will be a few standard OpenCL implementation that will cover most of the needs. You can rewrite an OpenCL implementation for AMD today with LLVM as it is. You can target directly the GPUs, and you have a few ways to dispatch kernels on AMD if you want to. So you don't even have to. You could I mean, that was Pekka did with the first implementation of HipCL, which was an OpenCL implementation for HIP hardware targeting HSA. It's in POCO, and he used it to implement HIP on top of OpenCL by targeting HSA and implementing OpenCL on top of HSA by using the AMD instruction emission backend. So I think the LLVM is changing a lot of things in the ecosystem, and maybe people have not realized that we have the power to do stuff that vendors contributed inside an LLVM, and is allowing us to target their hardware directly. So I believe in community project that will supplant in the future some of what used to be provided by vendors.
To provide a little more context why we arrived at the point where we have all of these complex multi-backend SYCL implementations. I completely agree that probably OpenCL is going to take a larger role here in the future once RUSTICL is stable and well-supported SYCL backend. And I think one of the reasons why we did this multi-backend architecture is to broaden the ecosystem, because it gives us access to things like cuBLAS. People want to call into an optimized BLAS library for their particular hardware, and with the current multi-backend design in SYCL, you can just take your SYCL object, turn it into a CUDA stream, a SYCL queue, turn it into a CUDA stream, and then pass that to cuBLAS and invoke cuBLAS if you want to run on NVIDIA GPU, and it will work. Now, in an ideal world, we wouldn't need to do that because we had native high-performance SYCL BLAS libraries that can completely replace vendor libraries. We are not yet at that point. Maybe we will be in a couple of years, and then I think there's even more of an incentive to focus in on OpenCL. At the moment, I think there's still a strong case for the current multi-backend architecture, but who knows? Maybe things will get more interesting in the future.